Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin wa bihi nasta'inu ala umuri dunya waddin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin nabiyina Muhammadin wa ala alihi wa sahbihi ajma'in. Amma ba'du. All right. Alhamdulillah, in this morning we can continue our discussion about new topics in competitive programming, which is about binary lifting. Okay, so before we start our discussion, let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul hazna idza syi'ta sahla. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. All right. So I think only four of you join the Zoom meeting, but are you in the same room with the others who is not joining the Zoom meeting? Okay, all right. Let's wait for them while we we start discussing. Okay, no problem. So let's begin our discussion. And I have created you a new contest. Yes, yes, Waalaikumsalam, Hayan. All right. So I think one of the senior students try to solve some of them. No problem. So let's talk about binary lifting. What is binary lifting? Binary lifting is an idea in graph theory, which is if there is a chain, for example, there is a chain, or let's make it vertically. If we have a chain and we want to move for some steps, for example, we want to move 5 steps, means go there. If we want to move 6 steps, for example, we will go there. Okay. So how to do how to do that? So at first, if we want to go to the next one by one, then it is so slow since the complexity is ON, linear to the number of moves. Okay, so how to do that faster? So in order to make it faster, we can we can create another edge which is going to step ahead for each node. And what if we store all moves or all steps? For example, from this node, we can move 1 here and move 2 here and move 3 here, for example, and move 4 here, move 5 here, move 6 here, and so on. If we store all of them, then when we try to jump for any step, the complexity is just O(n). But unfortunately, the memory to store them is O(n) squared. Why? Because for each node storing n nodes, storing all of the next nodes. That's why the complexity is O(n) squared. Alright, this is if we store all of them. If we just store one, then the complexity to move is O(n), but the memory is also O(n). Alright. Then how to make in the middle between these two alternatives? So don't just store one, but also don't store everything, but just store for each 2 to the power of something. So from any node, we will try to store what is the next node if we move 1 step and move 2 step and also move 4 steps and move 8 step and then 16 step, 32 step, and so on. So it means for each node, we just storing log n edges. That's why the memory become n log n. Alright. And then how to jump for specific steps. For example, you want to jump in 13 steps. What shall we do since we don't store this? But don't worry, we know that 13 is 8 plus 4 plus 1. And we know that jumping 8, we can do that in O(n). Yes, that's correct. After we jump 8, you know, in this node also storing all of the next node in 2 to the power of something steps. That's why we can move another step. We can move another 4 steps in just O(n). After that, we can move 1. Alright. So, you know, for each integer, we can convert it into binary number, and the number of digit is log n. So at most we need log n jumps in the worst case. So the complexity to jump for any steps is log n. So it is the combination of these two ideas, or the middle between these two alternatives. Alright, this is the middle way. And this called as binary drifting. Because we want to live from one node to another node higher than that, but we are not not moving one step by one step, and also not directly move at once, but we will move using this binary representation. That's why this idea called as binary lifting. Alright, is there any question about this? So let's read the first problem. So given a tree, or if we see the background story, given an employees and its employees has a boss except the general director, that is the root, and for any other employees has a boss, exactly a boss, not more than one. So the graph become a tree or rooted tree. All right. And then we need to process Q queries. For its queries given X and K, the question is who is employee X K level higher up. For example, if K is 2, then go up there. All right. For example, like this. Can be done with LCS, LCA, I think. LCS or LCA. Yes, LCA. Yes, the in fact LCA using paradrafting. So sorry, LCA is one of the application of paradrafting. So from this idea, we can solve some problem. One of them is LCA problem. All right. So LCA using paradrafting, and paradrafting can solve LCA problem. Yes, that's correct. So for this case, given the second employee has a boss employee 1, and the third employee has a boss employee 1, and then this is employee 4, employee 5. And then the question is, who is the first boss of 4? Of course, he is 3. And who is the second boss, or the boss of his boss? The boss of his boss is 1. Who is the general director? Next, who is the boss of his boss? Of course, there is no boss of general director. That's why just see out -1. All right. So is it understood? Yes. Okay. So we can we can solve it using parent lifting. So please don't go to the parent by one by one, since k is up to n, then n is up to 200,000. That's why we need to lift faster using parent lifting. So just start first parent, second parent, fourth parent, eighth parent, 16th parent, and so on. All right, so we can know the answer in just O log n query. All right, so is it understood? Right. So the implementation is like this. We know since the parent or the cost of each node is always less than that, less than him. And that's why we can directly create the ancestor. So we will create an ancestor maximum n, and also log maximum n is 2e5, and log is only 18. All right. Then if we imputing the parent, it means we imputing the first ancestor. And then what is the next ancestor? The second ancestor, the fourth ancestor, and so on. We can use this formula. Ancestor ij equal to ancestor of ancestor ij minus 1, j minus 1. Do you know the logic of this formula? Is it make sense? All right. So ancestor xy means the 2 to the power of y parent, or 2 to the power of y ancestor of x. Yes, just like sparse table. Then after that we can create like this. If we want to go up to the power of y, just move to the power of y minus 1 steps, and then moves another 2 to the power of y minus 1 steps. You know, 2 to the power of y minus 1 plus 2 to the power of y minus 1 is equal to 2 to the power of y. And you know, ancestor I j minus 1 means here. This is the ancestor I j minus 1. So ancestor of this in 2 to the power j minus 1 is here. All right, it's equal to ancestor ij. Okay. Okay, we can also do that, but since the constraint in the input, the parent is always less than that. So it means the parent already constructed. So the parent is the node before it. So the parent is already imputed. So he already has all of the ancestor. Also, and also this also has all of the ancestor and so on. So we can construct directly. Okay. All right. But generally, if the input is not like that, we need to input first for each node. After that, we will iterate from the log first. This is the more intuitive way. if it is not guaranteed that the parent is has a number less than him. So we need to iterate from this since it is always already computed before. But if it is guaranteed that ancestor is always less than I, so we can do this. Okay. But in general problems, we solve use this iteration. All right. After that, given Q query with X and Y, and we want to jump Y ancestors. The idea is we will iterate from log -1 until 0, and we will jump if Y is greater than that, or if the ith bit is on. Alright. If greater than or equal to this, it means this bit is on. That's why we will jump. Alright. Then just the out X. Okay, let's try to put the input. Try the symbol input. Okay, I think I can handle case -1. If X is equal to 0, then just see out -1. But wait, we saw input it starting from 2. Alright. Okay, now the output is correct. So generally, in order to make the implementation easier, we can create another node after the parent or after the root. So the node number is something, for example, 0 if the node in the tree starting from 1, or if the node in the tree starting from 0, then just make it n. And the parent of n is still n. That's why if we ask what is the ancestor, the 1000 ancestors of this node, then we will reach this since there is a self loop here. Just like this implementation, we assume that there is a node 0 above the root, right? If we make it -1 directly, then maybe we need to handle it in order to avoid runtime error. But if we make it 0, it is easier. Don't need to create any other branching here, but just create here when we need to output the answer. All right. Is there any other questions? All right. There is another idea to solve this. Do you know about EV-like decomposition? Have you ever heard this? Okay, just heard of it. All right. We will not discuss it much, but I will talk about it a bit. So we can solve this using HLD as well. So the idea of HLD is if we have a graph, we will create a chain from any node to its big child. What is big child? Big child is a child that has the most, yes. So HLD is we want to create some chain from a node, for example, from a root to its big child. Big child is a child that has the most number of subtree, the number of node in its descendant. All right. Yes, if you like decomposition, HLD. After that, of course, this node also has the next big child. For example, here, and then there's another big child until the leaf. Of course, the leaf has no child. All right. After that, the other node also has a big child, so we will create another chain. So the chain is like this. All right. Is it understood? Then, if two cells has same size, yes, choose any of them. Or maybe let's try to implement it. So at first, we want to input the parent, for example, like this. This is the parent of I. After that, we want to count the number of subtree. Plus plus, and then sub pi plus by sub I. If we know that pi is less than I. But if there is no constraint like that, then we have to do DFS or depth first search. All right. After computing the subtree, we also need to store the big child. So if sub I is greater than sub of big child of pi, means now big child of big I is I. All right. So we already know who is the big child for each node. A big child of a leaf is 0. All right. After that, we will create a vector of chain like this. So for each node, we need to store its roots. For example, root means the root of the chain. For example, the root of this node is here, the root of this node is here, this node is here. All right. The root of this is itself, and so on. All right. Of course, this implementation is harder than binary drifting, but I just want to explain another idea that can solve the other problem. All right. After that, after we got the chain, the idea is like this. Every node storing who is its root of that chain, and then we know what is the distance from the root to it. That's why we know what is the position in the chain. So for example, like this, we will iterate from 1 until n. If the root is still equal to 0, it means he is not in any chain. But if not equal to 0, then just continue because he is already in some chain. All right. If he is not in any chain, it means he is the root of itself. He is a root. He is a root, so just make it root I equal to I. And then just try to iterate. Starting from itself. And then go to it big child. To his big child until x is equal to 0. And always push back to x. So chain I push back x like this. After we push back x, just store this root x is equal to I, and then the distance to the root or the depth is j. All right. Is it make sense? Until x is 0, it means already reached the leaf. All right, so the code is like this. We have an array of integer root and the array of integer depth. Do you know what is the definition of both of them? Root means who is the root of the chain, and depth is the distance from the root to the chain. For example, the distance is 0, this is 1, this is 0, 1, 2, 3. All right, that's great. And then we also have a vector of chain. What is stored in that vector? The stored is in that vector is a vector consisting of the index of the nodes in the chain. For example, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then fact V1, storing 1, 3, 7, 11. And V6, storing 6 and 10. And factor 8, only storing 8. How about factor 9? Factor 9 is empty factor. So a node other than root storing no value. So just root that is storing the chain. All right. Is it clear? Is there any question? All right. So what for? So when there is a question as simple as this problem, for example, given x and y, then just do this. While y is less than or equal to the distance, the depth of x, when still greater than, all right. When still greater than, then y minus depth x plus 1, and then x is equal to parent of root of x. All right. And then when y is already less than or equal to depth x, then just see out chain depth x minus y. All right. Okay. And for this case, just check whether x is not equal to 0. If equal to 0, so just break, and then if x is equal to 0, then just see out minus 1. All right. This is not binary drifting, but it'll be similar. Okay, so we need to start the parent, and the memory complexity is just ON, not N log N, because we're only storing P and then size sub 3 and then big child and then root and depth and then factor of integer chain, total memory also ON. What else? So just try to run game. Wait. Okay. C8 root X. All right. 3, 1 minus 1. Yes, big means big child. What is big child? Big child is a child that has the biggest number of descendant, the biggest size of sub-tree among all of the child. All right, the answer is also correct. And the memory is better. How about the time complexity? Can you predict the complexity of this code? The time complexity, I mean. Here just On. This is also On. This is also On. Amortize. Since we only visit its node once. Yes, but for its query log n. Why this is log n in the worst case? Do you know how to analyze it or prove it? So the idea is like this. If we are in a chain and we need to jump outside the chain. If jump is only inside the chain, then just do this. So CA CH root X means the vector of chain in here. All right. And CA root X is here. And then if we access index depth X, it means here. If you want to jump Y steps, then just minus Y. All right. Minus Y, it means we already jump Y steps. Okay. But what if Y is greater than depth? Is less than or equal, it is okay. We can jump directly. But if Y is greater, it means we need to jump to the other chain. Is it correct? Because this is 3. There are so many chains, not only one chain. Alright, so we need to jump to the next chain. What does it mean? We already jump depth x plus 1. Depth x is until here, plus 1 means jump here. Depth x, we will jump until root x, and then jump another 1 step. It means we just use parent. This is the parent. Alright, so we will go to the other chain. Alright. And then we will still want to jump. If y is less than depth, alright, it is we can use this formula. But what if y is so big? So we will jump to another chain. Alright, and so on until we reach the node we want to find. Alright. So the complexity is equal to the number of jump from one chain to another chain. Alright. And we will jump from a chain to another chain is only when it is not his big child. It is not a big child. Alright. If it is a big child of its parent, so no need to go to another chain. But if it is not a big child, we need to jump to its parent. Alright. And if it is not a big child, it means the size of the size of subtree of this node is less than or equal to, actually less than, always less than the half of size of this node. Do you know why? So if the size of this is A, and the size of this is B, so B is always less than 8 divided by 2. Do you know why? We can prove it by contradiction. We can prove by contradiction. All right. How to prove it? Just prove. Is there any non-big child? Non-big child that is B is greater than or equal to A divided by 2. So we know there is no child like this. Since if B is greater than or equal to a divided by 2, it is always become a big child. It is impossible for the other child to have more than this. So now we know that for its non-big child, the size is always less than the half, the half of its parent. If less than half, it means when we jump always at least twice, and then jump at least twice, more than twice, and so on. So if we go down, divide by 2, and so on, that's why the number of jumping to another chain is just log n. Is it make sense? There any question? All right. So the complexity is log n. Okay. This is not binary lifting, but chain lifting. All right. And also sometimes binary lifting can solve a query. A query like this. For example, we want to find the sum of this until this, for example, or the GCD or the minimum or maximum. If the sum, it is quite easier because we can use prefix sum in tree. So we can do inclusion and exclusion. But what if the operation is minimum or maximum? We cannot use prefix minimum nor prefix maximum. That's why we need to use binary lifting. So just jump here and we already start the maximum for all of the path and so on. And also for this one, chain lifting, let's say it is chain lifting, we can also storing the prefix minimum, or sorry, not prefix minimum, minimum query. For example, we will find the minimum between this and this. We can use segment tree. So for each chain, we will store a segment tree. It means we can query there and also can update there. But if we use binary lifting, we cannot update. We just can query. Is it correct? Do you know? In binary lifting, we can query path like this, but not but not update them. Because if we update something, then all of the value will change. What is better? Then up to you. Which one is easier to implement? I usually implement using some segment tree. I think the time is faster for some segment tree for its EV path because the log constant is smaller. If we use a single segment tree, then the log constant is bigger. But if just like this, then the log is smaller. All right, and we can use the idea of dynamic segment tree, for example, in order to implement easier. we can implement using pointer to store for all chain, or even for it's not storing the same pointer. For example, we already create a segment tree. So for all node here, just point to this node. That's why all the node already storing the segment tree, just like persistent segment tree. All right. So we can do query and update. Okay. Is there any other question? Yes. All right. So let's continue to the next problem. So for the next problem, the tree is just same, but the type of query is different. The type of query is given to employees and who is the lowest common bus. So for example, there is an employee A and another employee B. Of course, they have some buses. So this is the bus of A, this is the bus of B, and the common bus is this, because both of them is the descendant of this bus. All right, but not for this bus, since this only has B but not has A. All right, so this is the common bus, and which is the lowest? The lowest is this. This is the lowest common bus. So it is just like lowest common ancestor for a graph. And we can find the lowest common ancestor using binary lifting, for example. Have you ever implement LCA before? Yes, all right. So I will not show you the implementation. And now, do you know how to find the lowest common ancestor using this? Using chain. All right. So let me show you the implementation. At first, we will start not the depth on the road, but the general depth. Yes, using HLG. We can also find the lowest common ancestor in O log n. So just make the depth is equal to, sorry, the depth of I is equal to the depth of pi plus 1. So depth is not local but global. All right. We can make depth 1 become equal to 0 or equal to 1, up to you. I think 0 is still correct. So it means it is not only depth x, and we need to change become depth root x. All right. Depth x minus depth root x. Yes, this is depth x minus depth root x. All right, this is when we want to find the y ancestor. But what if we want to find the LCA? We will do this. while root x is not equal to root y, then one of them will go up. But if they are same, just check who has the last step, the lowest step. Sorry. Yes. If depth x is greater than depth y, then just swap them. It means now depth x is less than depth y. So just see out x. Okay. And also about this, when the root is still different, then just check which one is the lowest step. If depth root x is less than depth root y, just swap them. Alright, now depth root x is greater, so it is safe if we want to make x jumping. Become b root x. Okay. Alright, let's try to input the sample. Alright, 311 is correct. Okay. Do you know the logic of this implementation? Okay, I think it is easy to understand. So just like binary drifting, we want to jump one by one until become in one chain. For example, he jumped there and then he jumped there. So finally they are in the same chain. So just find the upper one where the depth is less than the other. All right. So if depth x is less than depth y, so just see out x. But if depth x is greater than depth y, it means x is still here and y is here. Just swap them and then just see out x. All right. And how about this? So when the root is still different, please don't just compare depth x with depth y, but compare depth root x with depth root y. Do you know why? This is like this, for example, x is here and y is here. Which one we solve jump? The one at more depth, so we move. I think only to jump once more since we directly see out this. It is different with LCA where we just stop at a point before the LCA, so we need to jump once again. It is different. So if we already go there, the LCA between this and this is this. All right. Is it correct? Oh yes, that's it. Okay, yes. So why we compare depth root x, not only depth x? Yes, your sentence is correct. But why we compare root x instead of just x and y? Because if we just compare x and y, then for this case, y is more depth, isn't it? Then if we move y, then it is more than the lowest common ancestor, and the answer will be this, and this is incorrect. The lowest and common ancestor should be here. All right. But if we jump for the lower chain, so it is always correct, since if we jump there, it will be still not exceed LCA. All right. Is it understood? Okay. Yes, that's great. And we can also do the operation while we do LCA. For example, when we do binary lifting, we also finding maximum, for example. So we know the maximum in that path. And also for this case, when we jump, just query in that segment. All right. So we can do query update in a path. All right. And I prefer to swap them. So we just implement once. No need to copy paste between X and Y. Because sometimes the implementation is more than that. For example, there is an implementation of query and update, for example. So if we copy this and changing become Y, it is should be implemented twice. So sometimes we miss something. So this become a bug. That's why swiping is better. Even here, not directly C out X and C out Y, not like that, because sometimes it is not just C out, but also querying the path in the last chain. All right. Okay. Is there any other question? All right. So this is LCA, and the complexity is O n log n memory and O log n time. This is when we use binary lifting. If we use chain, then the memory is just On, but the time is log n. Do you know the other way that the time query is just On? Have you ever heard that? But the memory is n log n. So this one is better in the memory and this one is better in time query. All right, this is using range minimum query using using sparse table. Sparse table, but for storing range minimum query, not storing binary listing. Both of them using sparse table, but it is different. Do you know how to do range minimum query using sparse table? All right. So there are two type of sparse table. So sparse table means like this. For each node, it is storing this node only and then storing two nodes from this and storing four nodes from this and then storing eight nodes from this and so on. So we are storing for all 2 to the power of k. So when we want to query from L until R, a specific segment, then just use from L until 2 to the power of something, and then from R also with length 2 to the power of something before that. So starting from this and 2 to the power of k. So if we find the maximum of this and find the maximum of this and operating them, this just need O1 complexity. Is it correct? All right. So the implementation is quite same as sparse table in binary listing because we will do like this. For example, given an array of integer a. If we want to compute a sparse table, this is sparse table I0 means it means only covering one. Then just iterate from one until or from one until log. You know the value of sparse table ij equal to what? Maximum, for example, maximum between sparse table ij minus 1 and sparse table I plus 1 to the power of j minus 1. I think it is easier to do this. All right. Is the formula make sense? So sparse table form I with length 2 to the power of j plus 1. It is equal to 2 times 2 to the power of j. And it is equal to the maximum between this and this. This is from I 2 to the power of j. And then this is I plus 2 to the power of j. The size is also 2 to the power of j. All right, just like binary lifting. Okay. So how to use this to find the lowest common ancestor? At first, do you know about preorder? or Euler Turk. Do you know about Euler Turk? All right. So it is just like we do DFS while storing the order we visit the nodes. For example, the the tree is like this. If we do DFS, yes, in odd time, but we don't care about when it in, when it out, but we only care about the order. So we will create a vector storing the order we visit them. So for example, this is one. Visit one and then visit two and then visit four. And then we go back to two. Is it correct? We go back to two. And then go to three. And then go back to two. And then go back to one. Sorry, this is not three, but five. After that, go to three. And then go to six. And then nine. And then go back to six. Then go to 10. And then go back to six. So the number of occurrence is equal to 1 plus the number of childs. If it is leaf, it's only visited once. All right. For 6, then go back to 3, and then go to 7, go back to 3, and then 8, go back to 3, and then go back to 1. All right. Finally, we already start the order. And you know, the size of the order is n plus 1. So around 2n. Yes, around 2n. Maybe 2n minus 1. Okay. And in order to find the LCA, for example, LCA between 5 and 7. So LCA between 5 and 7 is a query from 5 until 7. Just find the minimum one. And you know the minimum one is 1. All right. Actually, we need to store based on the order of the visited. Not like this, but this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So just find the minimum between this. Which occurrence up to you. The first occurrence is okay, the last occurrence is okay. So for example, 2 with 6. It is up to you. Starting from this or this. Until 6, it is also up to you. This or this. But the minimum between all of them, always 1. Is it correct? Because 2 here is always still here. And if you want to go there, we will pass 1 without visiting upper than that. All right. So it is up to you, whether the first one or the last one. No need to avoid duplicates. Yes, no need to handle that. The order is always duplicate. And we need that duplicate. Why? Because if we want to find the LCA between 4 and 5, the answer will be 2. That's why we need 2 here. All right. For example, the ancestor between 6 and 7, the ancestor is 3. So we need 3 here. And when we find 7 and 8, the ancestor is also 3. All right. Okay. Is there any other questions? All right. So because we already compute the sparse table, so we can do range minimum query in just ON. All right. And this is the first type of sparse table. There is another type of sparse table which is storing a suffix from the middle and a prefix from the middle. So when we query L and R, just use this suffix and use this prefix. This is also ON. All right. But what if L and R is here? So we will divide again and then just conquer as usual. So the memory is just same and log n. And the time complexity is also O(n). Okay. And you already solve A and B. After that, how about problem C? Have you read this? Okay, yes, that's great. Is there any idea? No need to use weightlifting, actually. Is there any idea or observation? So the problem is like this. Given a permutation B and an array A. So for its query, given NLR, and the question is there any subsequence that is a cyclic sieve of P? For example, L and R is here. Is there any subsequence? For example, this one, 3, sorry. There is no subsequence, I think. But if we want to take this, yes, there is a subsequence, which is 1, 3, 2. This is one of the subsequence. All right. This is the subsequence, which is a cyclic sieve of this. All right. Cyclic sieve means the array is like this or like this or like this. We can sieve the permutation. All right. So do you know what is the idea? So the idea is like this. You know, in every cyclic shift, 2 is always, sorry, 2 is, he is the last value or before 1. Is it correct? And 1 is always the last value, or if it is not the last value, then the next is 3. Then how about 3? The next is always 2, or it is the last. All right. Do you know what I mean? Okay, so if we want to create a subsequence of cyclic shift of this or this or this, after 2 is always 1, or 2 is the last. All right. After 2 is always 1, and after 1 is always 3, or it is the last. And after 3 is always 2. If we want to create a subsequence, from 2 we will find 1 in the next value, and after 1 we want to find 3 as the next value, and so on. All right. So it means in this array, we want to find the next value of it. 1, the next value is 3 here. 2, the next value is 1. 3, the next value is 2. 1, the next value is 3. 2 has not, there is no 1 after that. So we can create a dummy vertex here. And also from T, there is no other value. All right. Okay, so we will create a graph like that. How about this case? 1 go to 2, 1 go to 2, 2 go to 1, but there is no 1. 2 go to 1, but there is no 1. All right, the graph is like this. All right, so the graph is become a tree. Is it correct? Because a node always has a parent after that, and then the last node has no parent. All right, so we can create a binary lifting for this. A subsequence is valid when from a node we jump n-1 times, or n-1 steps. After we jump n-1 step, it means it is a correct subsequence. Do you agree with this? Okay. Then do you know how to find if we start from this node, then what is the minimum n of the subsequence? How to find it? Then just jump n-1 step, isn't it? After we jump n-1 step, it means this is the end. How to jump faster? Do you know how to jump n-1 faster? Only to jump one by one. Yes, yes, start and end only. So In order to jump, yes, just use binary lifting with complexity or log n to find the n, and then just store the start point and the end point. All right. Just store all pair of start and end. All right. If we start here, where is the end? If we start here, where is the end? If we start here, where is the end? So we will just like creating a two pointer like this: start, start, and start, and start, and, for example. And sometimes we cannot start with this, so it is until the dummy node. And then after that, only until this, and so on. All right. If we reach dummy node, it means just delete it. Just delete them. And also if the next segment is less than this segment, delete it as well. Because it is not optimal. If we remove this, the answer is still same because we always have this. If a segment covering this, then the segment also covering this. Okay, do you know why? We just like to pruning for the segment. So the segment always increasing. There is no segment like this. There is no segment covering the other segment. If there is a segment covering the other segment, just remove it since it is not optimal. Not always independent, sometimes intersecting, but we can keep both of them if the case is like this, because one of them not covering the other one. But if the case is like this, then we can remove one of them. All right. Why we do this? In order make binary search is correct. So we can do binary search here. But if the array is not sorted like this, then it is hard to do binary search. So we can prune this, and removing this is not changing the answer, since alternatively we can use this. So just prune some segment that is not optimal. So the segment become like this. If the segment is sorted like this, so we can use binary search. For example, given a specific L, so it means the first segment we can use is here. So the last one should be at least here. So if R is less than this, so it means the answer is no. But if R is greater than this, so the answer is yes. All right. Is it understood? We can use Fenwick plus sorting. Yes, we also can use that. How to do that? What for using Fenwick tree? Sort queries. Okay, that's interesting. Yes, we can sort the query. So the query starting from this node or starting from this index and then starting from the next index and so on. So we can update one by one starting from the last, I think. Starting from the last and then just check or just find the minimum R. I think no need to use Fenwick trees. Just sort the query from start to end. Sort the query based on L is okay, based on R is also okay. So yes, all right. Yes, that also can be done. So I think the idea is like this. After we know for its start, where is the end, we can sort the query. For example, the query is like this. Input, input what? For example, the query dot first and then dot first dot second and then dot second is equal to the index since we need to start the index. After that, just sort them. We can sort based on L or based on R. Both of them are correct. We can also sort based on R if we want. So sort it by R. But if we sort it by L, is still there is a solution for it. And then just for from 1 until Q after we sort them. And then we also storing 2 pointers like this. So I think sorting by L is easier. But we will iterate from the last one. And also for this, starting from the last one. Then while j is still greater than or equal to si dot first. So let's change the minimum. Minimum is equal to the minimum between minimum and the n of j. The n index when we start from j. All right. What else? J minus minus. After that, what shall we do next? Okay, just find the answer. The answer of s1 dot second query is equal to, is the minimum is less than or equal to the second. All right, let's just see out the query. Yes, we can sort the query and do this. And no need to use value tree, I think. Okay, is it correct? Yes, in order to find a range whose start is less than or equal, or the n is less than or equal, just use min. Right, and just use two pointers. All right, is there any question? And before that, we need to find the parent. How to find the parent? I think we solved straight from the last one. We will store the occurrence. The occurrence of AI is in index I, and then the parent of I is equal to, or parent means the ancestor in 2 to the power of 0 steps, is equal to the occurrence of AI plus 1. I think not AI plus 1, but next AI. So when we input the value, we will do this input AI, and then occurrence I is initially n plus 1, and the parent of n plus 1 is equal to n plus 1 itself. And then the next of AI minus 1 is equal to AI. And the next of AN is equal to A1. All right. I think it is easy to understand. So that we will create a sparse table. So we know the parent of its nodes until n plus 1, I think, because we need node n plus 1 as a dummy node. Ancestor ij is equal to ancestor of ancestor I j minus 1, j minus 1. What else? All right. I think we want to find the n position like this. The end position is using planar lifting. As for j from log -1, j greater than or equal to 0. I think we can also starting from the lowest value if we use this formula. And this value already fixed. -1 and 1 shift left j. Yes, if it is true, then initially ni is equal to I. Turn that and I is equal to ancestor and I j. All right, is it correct? All right, just try to input the samples. Yeah, I think there is a difference between A and B. This is M, this is also M, this is N, and then we need to input array P. Then iterating this from M. And then this is until M. And how about this? This is also until M, but this is N minus 1. For that Q, and this is M, and this is M plus 1. All right, so we need this, and also occurrence and next, and also ancestor. All right, the max n and log is same. Let's try to input the samples. Hence is Boolean. I think it is not allowed to use next. We use NXT instead. One. Wait, let's try to output the N. 5 6 4 4 6 6 5. Okay, 4. I think not 4 since 2 should be equals to 1. So let's output the first ancestor. 3 4 5 6 4 4. 3 4 5 6. Okay, this is not n plus 1 but m plus 1. All right. Okay, now it is correct. Let's try to use the next input. Okay, this is also correct. Okay, is there any question for this problem? Yes, is it understood? Okay, but it is almost 9 o'clock, so you can try the rest of the problem, and this is also need to use pair lifting. So just create the edge, and then use pair lifting. And for this case, we will face the number theory problems. So we need to to think the analysis in number theory. All right. So there are some problem I have give to you, and maybe one some of them is too hard, and maybe I will remove some of them. But just try to read them first. All right. So I think that's all for today. Is there any other question before we close our meeting? I think it is enough. Yes, thank you very much for the nice discussion and for your attention. Let's end the meeting with praying kafaratul majlis. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassalamualaikum warahmatullahi wabarakatuh.